So we're starting lesson 811, which looks at putting horizontal shifts and horizontal stretches together with periodic functions. And that's why it's titled, How Can We Put Them Together? If we look at previous graphing of sine and cosine graphs, we've either done a period change or we've done a phase shift. We've never done them together at the same time. So we are going to examine that in this lesson. And then the next lesson, 812, is when we look at modeling using those. So let's just dive right in and take a look. And so in prompt 8.1, we're looking at transforming a sine graph. Okay, Laurel and Hardy are trying to write an equation of a sine function that has a graph that has a period of 2 pi thirds. That's important, and a horizontal shift of pi halves, units to the right. All right. So first, let's think about it. Laurel and Hardy. That's Laurel and Hardy, by the way. Laurel and Hardy, a comedic duo from a while back. But let's just not go into that part. But that's Laurel and Hardy. They're trying to figure this out. And I have certain pieces of information that are important to me. I know that I'm dealing with a period change of 2 pi thirds and a horizontal shift of pi halves units to the right. And so that's what I want to keep in mind. And so we are, again, trying to figure out who's going to be right. Laurel thinks that his equation is going to be sine of the quantity, 3 times the quantity, x minus pi half. So Laurel is using a lot of parentheses, and that's important. So I think maybe that's why he has a smirk on his face. Hardy thinks that he shouldn't be using that parentheses. I think that's why Hardy has that glare in his face. Hardy says his equation is sine of 3x minus pi half. It's a lot easier to say Hardy's, isn't it? So maybe that's why they're in disagreement in this case. But we're going to look at see who is right and who is wrong. In order to do that, we need to figure out what the similarities are and what the differences are. So first, what are the differences in these two equations? Well, if I look at it, Laurel has one extra set of parentheses. So let's kind of write that down. L of x, that has one extra set of parentheses. Okay, what else is different? Well, that means that Hardy's does not have an extra set. But here's what also is different is if I were to think about what that extra set of parentheses does, that 3 would be distributed to, or if I were going to distribute it, would be distributed to that pi over 2. But in Hardy's equation, the 3 is only being multiplied to the x. So there's another difference. And so we want to figure out who is right and who is wrong. And to do this, I'm going to go and I could put these in my calculator. I'm just going to go ahead and pull it up using Desmos. So if I have right here both equations, I'll quickly hide it. These are the two equations that we're dealing with. And so we need to figure out who's right and who's wrong. Well, what do we know? We knew that there was going to be a phase shift of pi halves. So I know I'm starting at pi halves, and I know it's a sine graph. So I need to figure out how do sine graphs start. And sine graphs start by being at the midline, and they are going to be rising first. So if I go to pi halves, which is right there, it looks like the red one is going to be the one that's rising first. The blue one looks like it's at pi sixths that it rises first. So something tells me right now, I'm thinking the red one so far is correct because it has the right phase shift. But I do need to look at the period change as well because it has a period of 2 pi thirds. And so if I have this, if I want to look at, here's where it begins at pi halves, and here's where the period ends at 7 pi sixths. So I'm at pi halves, and I'm at 7 pi sixths. Is that 2 pi thirds of an interval? And so that's what we're going to need to figure out. So let's kind of figure that out. So I have it here, and I took a picture of it. Let's drag it over there, and lo and behold, here it comes. All right, so when we're trying to figure this out, we know a few things. We know that we are dealing with a period of 2 pi thirds, a phase shift we already figured out. So here's my graph, and if I kind of think about it, I am starting at pi halves. So let's kind of move this out of the way, and we'll kind of write it down to the side of it. All right, so I'm starting at pi halves, and I am going to 7 pi sixths. That is one full period on the red. So is that 2 pi thirds? In other words, is the distance from pi halves to 7 pi sixths 2 pi thirds? It's hard to tell if they don't have the same denominator, so let's make it the same denominator. Pi halves is 3 pi sixths, and it's going to 7 pi sixths. So that interval, I would have 4 pi sixths. 3 pi plus 4 pi, 7 pi. Well, 4 pi sixths does simplify into 2 pi thirds. Alright, so the red one matches the characteristics that we needed in this. And that's the big thing we're trying to figure out. And so if I look again at Desmos for it, the red one is the one with the extra parentheses. Hardy is wrong. Laurel, the one that has the most parentheses, is right. And so we're going to examine that. That's the main idea behind this first prompt is, if you look, is which do we deal with? Because it does matter. If you look at it, if you have one less set of parentheses, it gives you a completely different graph. And so that's what we're kind of focusing on here, is we're trying to figure out what is going to be the most important thing. And so in this case, the good news is we know that L of x is the correct equation. I wanted to examine why, and so let's kind of write this down. So what is the correct equation? The correct equation for a trig function is you're going to have your a. It's going to be multiplied by, in this case, we're looking at sine. It could be cosine. I like to use a bracket, and then I'm going to put my b value. That was Laurel's situation. He had the 3 on the outside of a parentheses, and we're going to keep that x minus h, close the bracket, and then plus k. This is the general form for transforming a trigonometric function. Sine could be changed with cosine, even tangent, and it would still work. Alright, so let's kind of still continue with this Laurel and Hardy, because again, Laurel and Hardy, we know Laurel's right. Hardy's still upset because he can't figure out why he's wrong. And so again, we still have the smirky face from Laurel and Hardy that we're dealing with. So we're going through this, and it says examine Laurel's equation. For what value of x does 3 times the quantity x minus pi halves equals 0? You know, what's the horizontal shift? Note that this is asking for when the input of sine is 0, not where sine equals 0. Let's kind of focus on that. If I'm setting this parentheses equal to 0, I'm inputting 0 into sine. That's what that last sentence is telling us. All right. Now, really what that's also telling us is what's the phase shift. Because if I have 0, that means I'm starting from the original point. And you know, sine graphs start at, in this case, 0, 0, and then they start rising. So I am thinking about how do I get my input back to 0? And that's what this part is telling us. How do we get our input back to 0? Which means no change, whatever. But so we're trying to figure out, and if we do that, x would equal our phase shift. And that's what we're trying to figure out in this problem. Is what's the phase shift for Laurel's equation? And it's really the same situation for part B, but we're going to look at it with Hardy's equation. We're going to solve for x, which will be our phase shift. We're going to fill this in. So we're told to set the sine, the input of the sine, equal to 0. So here we go. And how am I going to solve this? Well, I just need to solve for x, right? Some people go, oh, I could distribute 3, and then I would, add over the 3 pi halves. But then I'm going to divide by 3. So I'm distributing 3 to the x, only to divide by 3 at the very end. Why not just divide by 3 right now? Because that would just cancel that out in the front. And 0 divided by 3 is just 0. So in that case, x equals pi halves. That's my phase shift for Laurel's equation. And in this case, remember your phase shift is going to be represented by the h value in your equation. So that actually is the same thing for Hardy's. The phase shift is going to be represented by the h value, what we solve for. But what's Hardy's phase shift? We did see, graphically, they're not the same. Do you remember where Hardy's equation started? If I go back to this, and I look at the blue one, and I go back to the beginning, where did Hardy's equation start? It looked like, for a sine graph, it would be either pi 6 or it could be 5 pi sixths. So I'm thinking it's going to be pi sixths. Let's take a look and see how we get pi 6. Now, I could add the pi halves and get 3x equals pi halves. Now, dividing by 3. is the same as multiplying by 1/3. Those are the two same operations, which pi halves times 1/3 is pi sixths. That's the phase shift of Hardy's equation. So we were right. Now, the reason why we're doing this is because we do have this general form. If we're thinking about graphing or even analyzing the graph, we're kind of like, hey, Laurel's equation is better. Because look at this. I can see the 3, and I didn't talk about how they got the 3 yet. Don't worry, I'm going to. And the pi halves is the phase shift. So Laurel's equation is a lot easier to read. If I had an A and a K there, I could do everything. Now, I did say I'll talk about it. I'll do it quickly. Is they both have the 3 in common, correct? They have the same thing, but one thing I didn't say up here is they do have the same period. If we go back to what B is, our period is 2 pi over B. And for both Laurel and Hardy's equation, your B was equal to 3. And so they both had the same period. That one we didn't analyze. Their phase shifts is what was different. So we're going to figure out how can we make Hardy's equation a lot easier to graph from. Well, we do know there was no amplitude change. So I'm just going to start with sine. I'll do my bracket, boom, boom. We know that their period was 2 pi thirds. They both had the 3. That wasn't a big deal. However, we learned Hardy's equation of x minus your phase shift is going to make it a lot easier. Well, we just found that Hardy's phase shift was pi sixths. So therefore, we have pi sixths. And there was no up or down movement. So the front page of the notes, the main focus was to get you to realize the general form and where each thing is. The extra set of parentheses is important for it. And we're going to look at the phase shift, and we're going to look at graphing these and analyzing these. So that was Laurel and Hardy's problem. The next video will go over and start at prompt 8.3.